Hello, I'm Piotr Mitros. This is my first annual thesis defense attempt. I'm going to talk to you about constraint satisfaction modules as a methodology for analog circuit design. What I mean by that is I'm going to show you how to design a family of blocks that you can plug together, and these blocks, they're based on constraints. So for example, here I have a block that holds x squared equal to y, and if you try to change y, it will change x. If you try to change x, it will change y. So they have a bidirectional flow of information. There's a local stability criterion. What I mean by that is that if you follow a methodology for designing these individual blocks, you can plug them in not quite arbitrary, but almost arbitrary global configurations, and the local stability criterion guarantees global stability. This is nice because it lets you build complex systems. In traditional analog circuit design, you have the problem that if you're trying to build a complex system, you need to do global analysis of every loop to determine stability. In this case, you don't need to do that. And so, moving on, I will divide this talk into 3 parts. In the first part, I will show how these blocks can be used to solve systems of constraint equations. So if I have a system like x squared equals y, x equals 8 times b, b is greater than 5, I can make a block that corresponds to each of those constraints, build a system that solves those sets of constraints. And this doesn't work for arbitrary systems of equations, but it works for a pretty large set. This is very similar to work that was done by Shua. He's a professor at Berkeley. The mathematics will be almost identical, although the flavor is a little bit different. And it's also moderately similar to work that was done by Jack Dennis at MIT a while before that. Once I've presented that, I'll show you how this can be used for modeling. So it will turn out that if I connect an under-constraint block to something that spits out values, so here I have a plant that's taking values of x and y. I'm looking at those values of x and y, and I want to build a model of how those relate. If I connect an under-constraint block, in this case y equals ax squared plus bx plus c, as it looks at values of y and x, it will build up a model of, it will build up what values of a, b, and c best model this element. Once I have a modeling block like this, I can use that to linearize the system. So this block is completely bidirectional. I can put a matched identical block, and this block down here will solve the quadratic equation y equals ax squared plus bx plus c. And thereby, I've got a model of the system. I'm inverting that model, and that way I can predistort to compensate for that nonlinearity. And this will either give one of the 2 roots, or if I want to, I can set that to give a specific root, depending on how I design that block. So this methodology came from discussions with Tom Knight. Tom and I were talking about an old methodology for solving systems of linear equations based on transformers. This was popular sort of in the 30s and 40s. It was created by a fellow by the name of Malik in 1933. Here, if I want to express a constraint like x plus y equals z, I can connect 2 transformers together, x across one, y across the other, put the other 2 ends in series, and that holds x plus y equals z. If I drive x and y, it will give z. If I drive y and z, it will give x. It's bidirectional. Overall system stability is guaranteed by passivity. If I want to have inequalities, I can put in diodes. He had a very nice paper on how to do this. Tom Knight, together with a student named Seidel, I'm not sure if I'm pronouncing that correctly, revived this in 1995. They used switched capacitor transformers to do the same thing. So Tom and I were talking about this. The first step that I took towards doing this, I moved this to active transformers. Now, when you're designing active transformers, you run into a couple of problems. One of them is you can no longer argue stability by passivity because, so if you look at this system, for the circuits guys, the computer science guys in the room can take this for granted. For the circuits guys, I have a gain of 2 from x to y. I have a gain of 1/2 from y to x. And if exactly what it should be, it will be a passive component and it will behave similarly to a transformer. If, on the other hand, I make an epsilon error, it will no longer be passive, so I need a different stability criterion. In addition to that, I can't use the exact transformer model because an ideal transformer guarantees that the voltage on one side will, in this case, be twice the voltage on the other side. But I can always take something like this, drive it with something stronger, hold both voltages to be equal, and then I need to output reasonable currents. So to solve those problems, I needed to make a sort of generalized active transformer. People have built active transformers before. This is yet another way to do it. The way that I did this, I took the transformer relationship, in this case y equals 2x, and I set up an objective function, y minus 2x squared, where this function is minimized when y is equal to x. At that point this is equal to 0, and otherwise it's positive, it's greater than that. And then the circuit just tries to minimize that objective function. The way that it does that is also pretty basic. I look at how changing the voltage on x will affect the objective function, and I output a current proportional to that. I look at how changing y will affect the objective function, and I output a current proportional to that. And indeed, this does behave like a transformer in that this current is double that one in amplitude. It's opposite in sign. It behaves just like a transformer. When the voltages are 2 to 1, the currents are also 2 to 1 in the opposite direction. So this is a little bit more general. I can build things that behave similarly to transformers that have more complex constraints. So this one holds x equal y squared. I can have very simple blocks, like this diode holds x greater than y, or a resistor holds x is approximately equal to y. And in fact, any component that circuits guys would call a passive two-terminal element, and that controls guys would call an incrementally passive one-port. There's a difference in terminology on what passivity means between circuits and controls. Any element like that is a valid constraint block within this methodology. So it's in a way a generalization of the concept of either passivity or incremental passivity, depending on whether your circuits or controls. I can plug these together into constraint networks. This time it's a slightly more detailed circuit. I added capacitors on all these nodes. Those capacitors are necessary for stability. They can either, in many cases, these can be just the passive capacitances of these blocks. In some cases, you need to put them in explicitly. And at that point, I will show how you can show stability of these systems. So let's take the system over here. I'll give a couple of definitions. As I said, each element has an objective function associated with it. So b equals to 5 might have b minus 5 squared. So this is, again, 0 when b is equal to 5. It could be to the fourth. It could be absolute value. Squares is a convenient one. I'll define the objective function of the overall system as the sum of the local objective functions. So the global objective function is the objective function of this, x minus x squared minus y squared, plus the objective function of that, x minus ab squared, plus the objective function of that, and so on and so forth. And in addition, I'll define the objective function around a node. So if I take the node B, that's just the sum of the objective functions of the constraint blocks around that node. Now, if I look at this, and I look at the current that's being output onto a given node, that current, by the methodology, is, from a single block, is minus dLi dVB, how the voltage on B affects this constraint. The sum of the currents onto that node from all of the blocks around it is just a summation of the ones from all of the nodes. Here, n sub B is the neighborhood of B. It's those three blocks. And if I look at the change of voltage on that node, that's just current divided by capacitance. So that's 1 over C times the current. So moving on, if I want to see how these, let's assume that for now, X, Z, and A are not changing, and I just want to see how the change on B affects the objective functions around the node B. So dLB dt is going to be the product of the rate of the change in voltage times how that voltage affects the objective function. How that voltage affects the objective function is just a summation of how it affects the local objective functions. So just the summation of dLi dVB around the constraint blocks around it. And so this overall change is the product of that, which we calculated to be 1 over C times this summation times this summation. We have 1 over the capacitance. That's always positive. We have these two, which are identical but opposite in sign. And so this is always less than or equal to 0. So you can see that the objective function node-wise is decreasing. The overall objective function is just the sum of those. So the overall objective function is always decreasing. And so by you can argue stability by either Lyapunov or LaSalle, and it shows that this will go to a local minimum. If there are many minimums, it might go to one of them, but it will go to a minimum and it will stay there. So if the set of constraints is convex, it will go and solve it. If it's not convex, it will find a minimum, and this works in the constraint case. By the way, if there are any questions, feel free to interrupt. This works in the over-constraint case, assuming a unique minimum. And now we can look at the under-constraint case. So let's say we have this active transformer, and it's just freely floating. If this loop gain is... Go ahead.
So you said the argument was saying you have all these terms which are negative, and when you take the sum of these negative terms, and so you get which is negative. So isn't this a little conservative in some sense?
It is conservative, yes. But it works. I mean, it just needs to be negative.
But you can force in locally everything.
Yeah, I mean, it's a local stability criterion. The objective function is decreasing locally. That's basically what lets me argue global stability from the local design constraints. So it is conservative, but it's not aggressively conservative.
So didn't the argument involve assuming that x, a, and b were staying constant? And they're not?
It did. If they're not, that doesn't... you basically end up with a second derivative term, and it ends up that you can basically you can ignore that.
You may have to make the capacity.
That's right. They require. You may determine the size of the capacitance.
Yeah.
That's the high frequency.
Oh, yeah, I should mention that for stability. So this argument shows stability in the ideal case. If you're looking at a real system, it won't behave exactly like the ideal case. There is a robust stability argument that I won't present. If somebody has a question, I can present it at the end. In addition to that, the way you guarantee high frequency stability is by making these capacitors very large. This argument at low frequencies doesn't depend on those capacitor values at all, and high frequency stability you can get by a variant of the small gain theorem. So if you make those capacitors as large as you want, you can make the gain, high frequency gain, as small as you want, and that guarantees high frequency stability. So moving on, in the under constraint case, what this argument shows by LaSalle's theorem is that we'll go to a minimum, but it doesn't say what the system will do within that minimum. So if you look at this, if the loop gain here is a little bit less than 1, this will go to, as we expect, in this case, this is solely the constraint at y equals 2x. It will go to y equals 2x equals 0. If that gain is a little bit more than 1, it will go to y equals 2x equals either the positive or the negative rail. And in general, when it's within the minimum, if you build a constraint block, it'll get to the minimum. But within that minimum, if it's a set, it may drift, it may oscillate, it may go to the maximum, to the maximum voltage within that minimum, to the minimum voltage within that minimum. You don't know what it will do. So there's a question, can we exploit this in an interesting way? And the way that we do that, let's take a block and assume here we have an under-constrained block. It's solely the constraint y equals bx plus c. And let's assume it's seeing three values of x and y. It sees y0 and x0, for instance, half of the time. It sees y1 and x1. Oh, that graphic is wrong. These two should be pointed in the same direction. It would always look at y0, x0, y1, x1, or y2 and x2. It would never be in this state. I apologize, that was an error. So let's say it looks at y0 and x0 half of the time, y1 and x1 a quarter of the time, and y2, x2 a quarter of the time, and we'd like to see what happens to the values of b and c. That's the same as if we had three blocks, one of them looking at y0 and x0 all of the time, one of them looking at y1, x1 all the time, one of them looking at y2, x2 all of the time, and if we just switch those blocks onto the nodes b and c with the same duty cycle, 1/2, 1/4, and 1/4. Now, if we do this switching adequately quickly, that the time constants of the switching are much faster than the time constants of the capacitors, so that between each switch, b and c changes a very small amount. This is the same as having three constraint blocks connected to b and c all of the time, just outputting half of the current, a quarter of the current, and a quarter of the current. And now we've gone from an under-constrained system that's looking at three blocks to an equivalent over-constrained system that has the objective function of it looking at one of the blocks half of the time, one of the blocks tailed by 1/4, and one of the blocks tailed by 1/4. So this is finding an estimate of the values of, in this case, b and c.
What about capacitance within the blocks? I'm wondering about the ability to split them into three like that.
The capacitance, you handle that. So right now we're operating at low enough frequencies that we're assuming the capacitors within the blocks are small compared to the capacitors outside of the blocks. We're assuming they're essentially instantaneous. And you can guarantee that it behaves that way by making the capacitances on b and c be much larger than the time constants of anything within those blocks. And that's essentially what we do. We make those capacitors really, if necessary, really big, and we make these things, the internal dynamics of these blocks, essentially instantaneous. So at this point, this builds a model of B and C. This will build a model at any point where this system of constraints is convex, and that's true for a large number of systems. One of the most useful ones is called general linear regression. For those, let's see if, just quickly check if I have anything else to say here. Yeah. General linear regression is a set of models that you can express like this. The summation over I of CI's, these are the model parameters, times some function of whatever it's modeling is equal to another function of whatever it's modeling. This includes a fairly wide range of models, including Taylor approximations, Fourier series, discretizations, wavelets, convex sections, Chebyshev polynomials. So this is actually a very broad range of models. For this broad range of models, we have another stability proof that I won't present unless someone explicitly asks for it. But it turns out that the system will also do modeling successfully here if it's changing slowly over, if those switches are switching slowly over time. And it's also, previously, it was robust in that if that switching was, it didn't need to be infinitely faster, but it needed to be very fast compared to the time constant of the capacitor. It had robustness in that it could be a little bit slower. I didn't present that proof, but again, if someone asks, I can present that. In this case, we have robustness in that it can fully converge one of the points, and it will behave in a fairly stable manner, meaning it will move around the optimum. So once we can build models, the next step is we can use those models to linearize things. So if we've got this nonlinear element, as I said, we can use something like this to build a model of that nonlinear element. These buffers are not necessary. I just added them to show direction of flow of information. You can either include them or exclude them. It doesn't matter. This will learn the values of A, B, and C. And this block down here will pre-assort based on those values of A, B, and C to control a linear system. Even though these should be matched blocks, the matching there is actually fairly hard to achieve in some cases. So looking back at our constraint blocks many slides ago, some of them, like the diode and the resistor, were symmetric. Some of them were non-symmetric. So the active transformer had a forward path, a backward path, and in this case you're trying to map the path from y and x to A, B, and C to the path from y and A, B, and C to x. This isn't impossible. It's moderately hard. There's a way to get around that problem and to make this whole thing more efficient by combining these two blocks together and essentially compiling it into a more efficient representation. So once we've designed a circuit under this methodology, it usually turns out that there's a lot of redundancy in the circuit. So if we have a couple of blocks, they're often computing the same functions, and you can do common sub-expression elimination. Many of the ports are known to be unidirectional, and you don't need to make a full bidirectional port. Very often these blocks will be monitoring the voltages around them, and will need a buffer to do that. You can use a common buffer that's shared among many blocks. Similarly, many of them do voltage load calculations. If you want to convert a voltage to a current, it's easier. You can save on space by having a single voltage to current converter and sharing it among several blocks by averaging the voltages. And there are also, in most cases, some approximations you can make and some simplifications that are specific to the circuit you're building. So we'll walk through an example of this. We'll model a nonlinearity by a second-order Taylor approximation, a simple quadratic. In this case, I switched x and y. And just to be a little bit more general, the notation that I'll use is that x is equal to the summation of ci fi, where f1 is y squared, f2 is y, and f3 is 1. And if we do this, if we were to take that constraint, put it in a least squares formulation, the currents that we would get out, I won't do the derivative, but if you did the derivative, the currents that you would get out would be fi of the output of the actual value of y times x minus the output value of y run through the model. So we can break this up into a direction term, fi of the value of the actual value of y that's being output, and a scaling term, which is the same for all of these blocks. So just carrying that on to the next slide, if we look at the scaling term is a pain to calculate because we need a large number of multipliers to compute ci times fi. And then we need to sum all of that up. It's a pretty big term. It turns out that if the model is monotonic, and here I'm talking about the model being monotonic, the system can be non-monotonic. If I have a set of models where some models are non-monotonic, I can just hook up a constraint block that will restrict the system to the space of monotonic models. I can make an approximation that the sign of that thing is just equal to the sign of the desired value of y, the input value of y, minus the sign of the actual value of y, the one that's being output by the system. The reason that this works, I won't explain this in detail. X is the desired value of y run through the model. This is the actual value of y run through the model is just this thing. So I'm running both of these through a monotonic function, and so it doesn't change sign. So the approximation that I'll make is I'll approximate the scaling term as that thing, and at that point the system becomes a lot simpler. This approximation loses in a couple of ways. At this point, at some points, let's say it's looking at those 3 points, the rate of descent at those 3 points may be a little bit different. And so this will no longer give you a least squares best model, but it will still be robustly stable. There's a second stability proof that I didn't show that shows that for cases like this, you still have robust stability. And in addition to that, how bad this change will be depends on how close the model is to being affine. If you have a fairly linear system and a fairly linear model, this and that will give you the same answer. And if the model is non-affine, the maximum amount of error depends on and the ratio of the maximum slope to the minimum slope of the model. That's actually a conservative bound, but it's a very tight conservative bound. So if we build a system to do this, this is the block diagram of it. It's pretty simple. If what it's doing here is that comparator that's calculating the desired value of y minus the actual value of y. This is integrating to get C1, y1 times the desired value of y minus the actual value of y. This is integrating the actual value of y times y desired minus y actual. This is integrating y actual squared times y desired minus y actual, so that's how you're computing that. And this is just a feed-forward calculation of playing the model through to try the system. It turns out, I won't explain why unless someone asks us a question at the end, that this eliminates the matching issue. If there's a mismatch between this and that, assuming enough signal diversity, this will actually still converge to very close to the right answer. And it's also a lot easier to match these blocks since now these are identical blocks. If you build a circuit to do this, this is a circuit that I built to do this. It has just over a dozen components. It's building a second order, over a dozen major components, so multipliers and op-amps. It's building a second order Taylor approximation. There's a little diode there that restricts it to the space of monotonic models. That's a attached constraint block, as I mentioned. It's not fully restricting it, but it turns out that it stays there. This has about twice as many op-amps as I need. This was the circuit that I built to characterize performance. So I wanted to be able to monitor current levels, voltage levels, things like that, easily adjust gain. So if I were to take out the unnecessary components, it would have just under a dozen major components. If you look at how that behaves, the nonlinearity that I was looking at, I was swapping in and out a diode and a voltage divider, so it was just adding a kink. Without a nonlinearity, the input was tracking the output. There was a very small amount of error in the square term. If I swapped in the nonlinearity, the instant I swapped it in, I would get a large kink, and then the system would adjust, build a model of this, and then compensate for that. And so it would adjust to minimize that error. If I swapped out the nonlinearity, it would have a bad model. So again, the output didn't track the input. These don't overlap entirely because the system is learning as it's doing this. And then in the steady state, it would go back to that. This circuit in a more generalized form, the way that it looks is I have a column for each term of this model. And let's say that I was to build this in an integrated circuit, build a complex system like this that had, say, 100 columns or a large number of columns. These columns are pretty easy to build. These multipliers, you can just use a Gilbert cell for. They don't actually need to be very good. Only performance around the origin matters a lot. Otherwise, the error that you get from that is pretty small. If these functions, they need to match. If they're not very well implemented, it's just going to build a model with a different set of basis functions, but the model will still be pretty good. So this is actually a pretty simple circuit to build. Let's say I've got 1,000 of these columns. If, let's say, one of them fails. If it fails in an unclean way, so let's say this column fails and it outputs an oscillation, there's nothing I can do about it. If it fails in a time-varying manner, there's not much that I can do about it. But if it fails in a non-time-varying manner, so it pins to one of the rails, it pins to ground, or it outputs some function of y desired, it turns out that what will happen is the other blocks will just take that as part of the model. They'll just treat that as part of this nonlinearity, and they'll compensate for it, which is a very nice property. In digital circuits, we're coming up with Moore's law to the point where we're expecting devices to fail. So if you look at a device of maybe about 1/10 of a micron, it'll have 150 atoms of dopant in the channel and a standard deviation of 20. As that gets smaller, the number of dopant atoms gets smaller, and we're getting very close to the point where we're expecting some devices to fail. In digital, people are building methodologies where they have digital error correction through the logic that people are expecting will be necessary a few years down the line. analog isn't there. Analog has not really kept up with Moore's law scaling for a number of reasons. One of those is analog circuit design methodologies don't do very well at designing complex circuits. People tend to build, for instance, if you're trying to improve the matching between two differential pairs, you just build very large devices, essentially put a bunch of things in parallel, as opposed to putting a bunch of different things in parallel and using that to get better performance as well. And if analog was actually following Moore's law, we will be very close to that limitation. Well, we might get close to that limitation in analog eventually as well. So robustness is kind of a nice property. There's a bunch of future work that needs to be done. One of the major ones is developing applications. This sort of breaks down into two parts. High-level applications, so new uses for this methodology. I showed how this can solve systems of equations so long as the objective function is convex. I showed how this can be used to linearize for some set of models, or model for some set of models, to linearize. It's likely that there are other uses of this as well, especially if you look at presenting inputs at a rate that's not either very fast or very slow, but in between. It looks like there might be some interesting behaviors there. If the constraint blocks themselves are time varying, or if you have constraints on things that are other than raw voltages, if you can come up with a way to, for example, set up a constraint x squared plus y squared equals 1, dx dt squared plus dy dt squared equals 1, and try to build things like oscillators there, it looks like there are plausible ways to potentially have more high-level applications. We want to develop applications for sort of the existing uses of this methodology. So for instance, you can use this to build a superior operational amplifier. If you look at an operational amplifier, you have variations from device to device. Dopant levels vary, oxide levels or oxide thicknesses vary, things like that vary, temperatures vary. A constraint block like this could potentially do an optimization problem to calculate optimal bias levels to compensate for that. A modeling block could model this distortion of a given stage. Here the modeling block doesn't need to run at the full speed of the op-amp, it only needs to run at signal speeds. It could model the distortion of individual stages of the op-amp, and at that point you could adjust bias current levels to try to minimize that distortion and maximize gain. Once you're doing that, you can think about modifying those stages so that you actually have control over the distortion. So you can, for example, instead of making a stage that's 10 devices wide, make 10 different stages and adjust the bias current levels to them, sort of to take a combination of those stages that minimizes distortion, possibly even put in a few stages backwards that have low gain, high distortion to subtract off some distortion, and try to linearly combine those stages to minimize distortion. There's obviously some hard engineering problems to doing that, but that's a reasonable use for this. And you can even think about doing things like trying to use a modeling block to model the relation between those bias currents and this distortion, and that gets to be a really hard engineering problem because you're dealing with very different time constants, and you're dealing with some problems with presenting enough signal diversity to the modeling stage. This looks like it has applications to controlling a nonlinear system with a time delay if you're trying to compensate for the nonlinearity as opposed to a disturbance. So if you do this with a traditional feedback loop, it's a hard problem you're fundamentally limited in feedback loop performance because of the delay. If you build a model of it, it works a lot better because, well, you don't run into that limitation. And one example of this is called Cartesian feedback. In Cartesian feedback, this is a technique that's used for RF amplifiers. In Cartesian feedback, what you do is you take the signal, you modulate it, you run it through an output stage, you demodulate it, and you feed back to make sure that the output signal tracks the desired input signal. The feedback loop there is hard, and there are people like, for example, Joel Dassin at MIT working on building various types of models of a system like that so that you calibrate this once, you figure out what input you need to have to give a given output, and then you play back those inputs from a digital memory. This is very useful in RF because, as I said, there's a delay in the system, there's a modulator and a demodulator, and in the RF stage, if you have a very linear gain stage, it has high distortion. Sorry, if you have a very linear gain stage, it has very bad efficiency. If you have a very nonlinear one, you can make it high efficiency, but it's hard to do both at the same time. So this could potentially be used as a modeling technique there. Sort of theoretical extensions to this are to control systems with memory. There's two sort of major ways that you can push to do that. If you build a very simple model, y equals epsilon x plus b, and if you take that model and you replace the capacitors on those nodes with a filter, you can build an arbitrary LTI controller. So there's a sort of natural way to integrate LTI controllers into this nonlinear control technique, but the math there gets very hard. I have not been able to work it out, so that's an area of future work. More easily, you can use the system to build something similar to a Kalman filter to build a model of a system with dynamics, and at that point, you can also think of using this to control systems with dynamics. In addition to that, when I was working on designing this, I was trying to make this as simple as possible so it can be a building block for other analog circuits. I wasn't pushing this as a competitor to digital. I was pushing this as a building block for analog circuits. So there's a lot of places where I traded off performance for cost in favor of low cost as opposed to high performance. And there are ways to increase performance by the use of parallelism. So if you look at several samples at once, as opposed to just one sample, or by having a dynamic integration rate. So right now, those capacitors that you saw are very conservatively set. They're a lot bigger than they need to be at most bias points. If instead of that, you control the rate of integration dynamically, you can get much higher rates of convergence. And once the system has converged, if you can lower it, you can get lower noise, better noise rejection. So those are sort of the areas of future work. So what I've shown you today is a methodology for analog circuit design. It has a local stability criterion. It's based on bidirectional blocks. I've shown you how to use it to build equation solvers, how to use it to build models, and how to use it to linearize nonlinearities. And now I'll open up for questions.
Any questions?
I have a
Go ahead.
question. You've spoken about the signals in the system as being sort of all voltage-oriented signals, but you can obviously apply a dual to this system. I'm wondering if you'd thought about, going to a version where, the signals were the currents and the voltages were the error terms essentially.
I have not thought about that very much. There was an interesting paper that I saw that made an analog to switched capacitors with switched currents. The reason that I haven't thought about that very much is with currents, it's a little bit, the equivalent of a capacitor for a current is an inductor, which is sort of a pain in the ass to build for analog systems. There are active equivalents, but if you use those, I think that you would lose a little bit in terms of performance or complexity. And I think more to the point, I had not thought about that very much. The switched current techniques that I saw were also fairly, I would say, they had fairly low accuracy. The switch and the actual current mode techniques have very high accuracy, but again, you've got the inductor problem. You had a problem? You had a question?
So let's say every local block has some big intentional capacitors and some internal parasitics within it. So I could imagine that if you hook up a whole bunch of blocks together, depending on the nonlinearities, depending on the interactions, you may need to be much more conservative in certain parts of the computation and much less conservative in certain others. Do you have any theorems or thoughts or analysis on how that will scale? For example, I could imagine that everything was linear, just dominant pulling every local node would suffice. But if it's nonlinear, that's not necessarily obvious how you do scaling. So do you have any thoughts on, for example, if the intentional seeds were sufficiently larger than the sum of all the internal parasitics, the root gain of the linearized group or something, you're guaranteed convergence because you have enough phase margin. Do you have any theorems or any?
Yes. The basic way that you look at this, so the way that you analyze, so the first thing that you need to do to look at that is robust stability. So stability, when you have small errors in what the currents are output, that they're not exactly dL, dV, but that they have a small error. And the way that you look at that conservatively is your steepest descent gives you some size vectors. Let's say we can place a bound on those error currents. That gives you a region within which the system no longer behaves sort of near the plateaus, where the error currents might be larger than the intentional currents. When you have that region, the short story, I can go into detail, but this is not really relevant to the question, is you end up with a slightly bigger region that the system is guaranteed to converge to. And what you do at low frequency, what you do is you decide how big you want this region to be, and you say that that region, this will hold up to some speed without, just not looking at capacitors, it's hold up to some speed. Then when you put in the capacitors, what happens is you have a I apologize. I should have a better way to do this. But
If you press the number in the slide into it, everything changes.
I'm not actually using Acrobat. I'm using XPDF, which is not very good for presentations. But it turns out you've got gains from nodes to other nodes, and you're trying to, it turns out that there's a bound on basically these local gains that from every node to the nodes that are one block away from it, that if those gains end up being less than 1, the sum of those gains end up being less than 1, the system ends up being stable at high frequencies. So there's a theorem like that. It will take you a moment to re-derive it. It's basically based on a variant of the small gain theorem. It's essentially the same argument as the small gain theorem. It's a little bit more, there's a little bit of a variation because you've got gains coming in multiple directions, but it's essentially the same as the small gain theorem, and it's essentially a local criterion. Any more questions?
Yeah, I came a little bit late, so you might have covered this. I mean, how does this relate to Jack Dennis solving mathematical programs?
Jack Dennis's work, it's his work, the circuits that result from his work are simpler than the circuits that result from my work, but they're less general. If you look at Jack Dennis's thesis, he essentially covers linear mathematical programs. He doesn't cover, he sort of pokes at different ways how he would go about nonlinearities, but he doesn't go into the full set of nonlinear systems. And this has more complex circuits that handle a broader set of cases.
So you can solve convex programs? Is that right?
I can solve general convex programs with this, yes. Chua did work that can also solve general convex programs that's very similar to this. That's much more similar to this than Jack Dennis's thesis. And the way that it differs from Chua's work, basically, after the first bullet, the time-varying things are very substantially different from Chua's work.
So this might have been implicit in the other scaling question you got, and I just didn't understand it. But if I had, say, a high diameter network with thousands of these little constraint boxes, will this scale to handle those sort of large networks as well?
It will scale in the sense that it will be stable. The bounds on convergence times, as it gets more complex, the convergence times go down fairly quickly, which is sort of a pity. But in some cases that matters. What? Sorry, go up. it gets slower, which is sort of a pity, but in some cases that matters more than in others. So long as the local constraints are pretty close to being met, it might be okay.
That maybe plays into the other half of the question I was wondering about, which is, are the sorts of nonlinearities that you can deal with complicated enough that you can end up encountering NP-ness in the constraint solutions that you
This is not a proof that P equals NP, no.
No, I wasn't asking that. That was actually more a question of, might the convergence, is it complex enough that the convergence times could get badly spiked if the constraint system that you're solving is related to one of these NP-nasty constraint problems?
In general, the NP-nasty constraint problems are non-convex. If you look at something like 3-set, it's non-convex. So what the system would do if you gave it 3-set, it would converge quickly to a minimum, but not to the optimal minimum. So it doesn't actually get into that sort of NP-nasty convergence time to the case, at least in the cases that I've looked at, but it does just not address those systems.
Just a basic question. So, how, as I understand that the action of the circuit, you're trying to do gradient descent on least squares objective. How does the circuit behavior change near non-differentiable points? Like your example, nonlinearity had a diode.
So a diode is actually quite linear. It has an exponential, which is nice. And the practical issue, anything that I build in a circuit, I can't physically build a hard kink in a circuit.
So there's going to be some like so what's the frequency component in some sense? Spike.
So it's, basically, I can't actually not get steps in a physical system. So I sort of don't address that. There is a paper that was written, I think, 5 years ago, where a guy in Taiwan generalized one of these mathematical program solvers to handle things, the mathematics to handle disjoint sets, but it's, from an engineering point of view, basically useless because, it's a pile of math that doesn't actually buy you anything for engineering.
I guess I asked because that I wonder if I took a 3-set problem, my nonlinearities are going to have boatloads of diodes, right? And in some sense, you're going to be doing gradient descent on a funny smooth version of the 3-set.
Oh, in general, so if I take 3-set, the way that I would normally set that up as an optimization problem is I would replace the multiplier, I would replace the AND gates by multipliers, the OR gates essentially by adders, a slight variant of adders, and at that point it becomes quite continuous. It becomes a continuous system with a large number of minima at various intermediate points. That's sort of how usually I would convert that.
So we've managed to create some interesting new analog circuitry by taking transformers seriously, probably for the first time since the 30s. What happens? Is there extra power that would come from thinking about some of the other more or less passive components like gyrators?
Sorry, you said gyrator?
Yes.
I don't know how gyrators would fit into this methodology. This methodology, it's in one sense a generalization of passivity, what circuits guys would call passivity, meaning no gain, what controls guys would call incremental passivity. But in some very real sense, it's not. I can build systems if, for example, I was to take out those capacitors that I have there and replace one of these guys with an inductor, the system, I can build non-stable constraint blocks. I can build a constraint block that, well, I don't need that anymore. I can build a constraint block with just two terminals that if I connect a capacitor and inductor to it on one side, will oscillate. So it's not a complete generalization of passivity. It's a generalization of memoryless passivity, I guess.
Well, if there are no more questions, I suppose we kick everybody out except for the committee. Thank you for coming.
Thank you.